Good evening everyone. In this video we are going to discuss about deadlock detection. The deadlock detection, two different way we can able to identify. If the resources are having only single instance, that is single instance in the sense only one count. If the all the resource type it is having only the single instance, so then we can easily identify the deadlock detection. So using the resource allocation graph with the variant version of that is called as a wait for graph. So we can obtain this graph from resource allocation graph. We can remove all the resources and the edges are going to be collapsed with the appropriate edges. So we will get the wait for graph. So this is our normal resource allocation graph. So we know very well. Here the process, the circular indicate by the process or threads, and rectangular boxes it is indicating as a resources. This will be indicating this is request age. The T1 thread is requesting for the R1 resource. The R1 resource already assigned to the T2. Now, how the wait for graph we need to construct in the sense we are going to removing this R1 resource. So the arrow mark will be going to be combined like this. So T1 to T2 because the R1 is assigned to the T2. It is given to the thread 2. If the thread 2 completes and releasing the R1, then only the T1 can able to execute. So the T1 process, that is a T1 thread, it is waiting for T2. So that is the meaning of the wait for graph. So in the wait for graph, the arrow mark is indicating each and every thread is waiting for another process. So according to this scenario, the thread T1 is waiting for T2. So T1, T2 completes, it is releasing the R1 resource now, then only the T1 can able to execute. So similarly, the T2 is waiting for T3. T3 is wait for T4. T4 is wait for T1. So we already know about if the resource allocation graph contain any cycle, so then there is a chances for the deadlock. So here the same thing. In the wait for graph, if we are having a cycle, then obviously, so it may lead to the deadlock. So here T1 to T2, T2 to T3, T3 to T4, and T4 to again T1. So here the cycle is there. So there is a possibilities for the deadlock detection. If the resource types are having only single instance, this will be applicable. If it is a multiple instances, so then what we can do for that? So the multiple instance means the wait for graph concept will not applicable. So we have to apply the deadlock detection algorithm in that cases. So this is our deadlock detection algorithm. So by 4 steps. So initially we are just assigning work equal to available. The loop will be executed for the all the n number of the process. Then we are checking the finish of stated whether equal to false. Then we are checking the request of I must be less than or equal to work. If the both the conditions satisfied, then third step will be executed. Then finally we are checking all the finish of I equal to true means then the system is in no deadlock. If any one I process it is equal to false means, so then we can conclude. So there is a deadlock for that I process. So now we can solve with this example. Here the allocation matrix is given, request matrix given, and then available matrix is there. So now we can apply one by one. The first step, work equal to available value is 0 0 0. As per this scenario, all the resources are allocated, so there is no availability in our hand. So then the finish of I, all the threads we must indicate it as a false state initially. The next step, the condition finish of I, that is a finish of 0. The loop will going to execute for I equal to 0. Finish of 0, whether equal to false or not, is the condition true. And now the second condition is request of I, that is request of 0 must be less than or equal to our work. So request value is in this matrix is available. The request of 0 is again 0 0 0, that must be less than or equal to our work, or work value is also 0. So both are equal. Now the condition satisfied. So then the third step, work equal to work plus allocation of I, that is allocation of 0, work value is 0 0 0, allocation of 0 is 0 1 0. So our work value become 0 1 0. Then immediately we are just changing the finish state. Finish of 0 will become as a true and remaining or false. 1 2 3 and 4. So then the loop is going to execute for the next I equal to 1. For the I equal to 1, again the same steps going to be repeated. First condition, finish of 1, whether equal to false or not, is the condition true. And then request of 1 less than or equal to our work. Previously we updated the work value. The request one is 202. That must be less than or equal to updated work value is 010. Here the condition is failed. So test 1 can't able to execute, it must wait. And then loop I equal to 2, finish of 2 equal to false, and request of 2 less than or equal to our work. Request of 2 value is 0 0 0 less than or equal to 0 1 0. Here the condition true. Both the conditions are true. Now work equal to work plus allocation of 2. So now the work value 0 1 0 plus allocation of 2 3 0 3. So the work value become 313. And immediately we need to update the finish. So 0 already 1 false, and then now 2 will become as a true, and 3 is false, and 4 is false. Then for I equal to 3, finish of 3 equal to false, is the condition satisfied, and request of 3 less than or equal to our work. Request of 3 is 1 0 0 from the request matrix, less than or equal to our updated work value is 313. Is condition satisfied. So we are updating the work value. Work equal to work plus allocation of 3. So now work value is 313 plus allocation of 3 is 211. So now work value will become 524. Then immediately the finish matrix must be updated. So 0 already true and 1 is false, 2 is true and 3 is true and 4 is false. So the next I equal to 4, the same condition, finish of 4 equal to false and request 4 must be less than or equal to work. First condition satisfied. Request of 4 is 002. Work value 524. Condition satisfied. So work is going to updated. Work plus allocation. So work is 524 plus allocation of 4 is 002. Now the updated work value is 526. Then the finish must be updated 0, 1, 2, 3, 4. 4 now will become true and 0 is already true. 1 is false, 2 is true and 3 is true. So now again the condition is going to execute. The loop will be executed I equal to 0. Now finish of 0 whether equal to false. So here it is true. So the condition is going to getting fail. Then the loop will going to execute for I equal to 1. Finish of 1 whether equal to false. Yes, condition is true. Then request of 1 must be less than or equal to our work. Request of 1 is 202. Now the updated value of work is 526. Condition satisfied. So work equal to work plus allocation 2 plus 526 plus allocation of 1 is 200. So updated work value is 726. So similarly we need to update the finish 0 already true. Now 1 is become true and 2 is true and 3 is true and 4 is true. So if the finish vector, if the all the threads or process will become true means, so then we can conclude no deadlock. Suppose any one thread still it is not changes its state from false to true means, it is maintaining the false means, so that particular thread it is leading the deadlock. For example, the after executing the loop, the thread 1 still in a false means, other remaining its true means, so that process 1, that is a thread 1, it is leading the deadlock. So like that we can conclude. So this is our deadlock detection algorithm when we have a multiple instances on the each and every resource type. Thanks for watching.